Hello, everybody. Sorry that I'm late. We had daylight savings time here in the U.S. and I didn't realize you guys don't practice that, so my clock is an hour. It's like 9:16 here. So let's go ahead and get started. I apologize for that. All right. So, all right, here's our lesson. As usual, if anyone has any questions, you can leave them in the chat. If you can't hear me or anything's not clear on the screen, also let me know in the chat. I'll check it from time to time. Okay, so today we'll get started on our third class of partial differential equations, and those would be hyperbolic. So if you remember, we already looked at the elliptic and parabolic, which were two of the examples of that were the distribution of heat and the conduction of heat. So we'll look at a PDE that goes for hyperbolic today, and this will be the wave equation. And we'll discuss its numerical solution using the finite difference methods that we've been using up to this point. So let's go ahead and get started with that. The wave equation is a fundamental PDE, and it describes the behavior of waves in various physical systems. So, for example, you might want to track the waves that radiate out as you drop a pebble in still water, right? You could track those using the wave equation. More complicated, you could find solutions that describe the wave of a violin or a guitar string when you pluck it, or a wave of acoustic sound vibration going through the air. So this has some of its own uses. It's a pretty good equation to work with and to know how to solve. As usual, we will use the finite difference method. So, we look at central differences and we just use them twice because we have the time index as well. So we have to have one dimension for time and one dimension for space, as we saw before. And the normal finite difference method that we get when we use the Taylor series truncation or the Taylor polynomial to approximate the derivatives of functions. In this situation, the central differences will be applied twice, so we'll use these to approximate the space derivatives. And then we'll add a time-stepping formula to advance the solution in discrete time steps. So we'll go all through that, and we'll see how that works. And then we'll show how to initialize the stepping process and update the solution at each time step. And then finally, we'll look at a function. The initial code of this function was in Julia, but this code will be in Python. After that, we'll look at some stability. Remember, we've talked about stability before, but it's good to just have a good understanding of that. This is a crucial aspect of numerical methods for solving PDEs. And we'll look at this thing called the CFL condition, which is CFL stands for Courant, Friedrichs, and Louis. And this is a condition that it's a stability criterion. So it tells us, the stability of our solutions. And what's nice is in particular, it applies to hyperbolic partial differential equations. So, and then we'll show how to apply it. So we can go ahead and kind of start here, and this will lead us into the rest of the talk. So let me just check if there's any questions or comments in the chat. Okay, good. All right, so we'll discuss how to apply this condition to a numerical solution, and that'll help us to guarantee stability in whatever simulations we're doing. So for the wave equation, what we want are functions u of x, y as solution to a PDE. So this isn't the wave equation here. We'll go over that, but this is the way that we describe in general what we're trying to do, right? So we have second partials, or all the mixed partials here, as A, B, and C. So if we have an equation like this, and then we add to that some function of the first partials along with the initial variables and u itself, right? And that's just some relation in the sort of the vector space of PDEs, and we set that equal to 0, and that would be whatever solves that relation. That would be the things that are the solutions to our PDE. In this case, x and y are independent. You could probably tell that. And then I just wrote down the notation in case some of you don't remember, but ux, uy, uxx, uyy, and uxy. So when we have a second order PDE like this, where we have A, B, and C as these coefficients, we can actually check something similar to the discriminant from your high school algebra classes, so the quadratic formula. And what we'll do is just look at what does it mean when this discriminant takes on different values. So if b squared minus 4ac is 0, then this is a parabolic. It means it's like a heat type equation. If b squared minus 4ac is greater than 0, then it's hyperbolic, like the wave equation, which we're going to talk about. And if b squared minus 4ac is less than 0, then it's elliptic, which is steady state. And we've already spoke about those too. So that's the way we classify the second order PDE. All right, let's see if we've got any questions again. Okay, so hopefully everybody can hear okay, and there's no issues with the video or sound. All right, so let's talk about the wave equation now. So a wave is propagating in an interval from A to B, and the independent variables are x in AB at time t greater than or equal to 0. The wave speed will be c, constant greater than 0. And I gave you some different examples, but one example is the wave equation models the oscillation of a violin string, right? And then it has this form. So these are the relations that we use to solve this PDE. So in this case, I'm just doing one-dimensional, right? Because my x is in an interval and not like a square or a ball or something. So we have UTT is equal to c squared uxx, where when t is greater than or equal to 0. ux0 is equal to f of x for all x in AB. So if I fix this, I can sort of think of this here as time, right? We said we wanted a solution uxy in the previous slide, but I can also just imagine this as the time parameter, and then this one as the space parameter. So it takes in ordered pairs where the first component of the ordered pair is the space parameter, and the second component of the ordered pair is the time parameter, right? So that has to be equal to a function if I set t equal to 0 for all x in AB. And then the same thing for my time derivative itself. So not just the function, but the time derivative itself. It has to be equal to another function. And this is sort of an initial condition kind of thing that you can imagine here. Also, we have that uat is equal to phi of t. So at the end point, it has to be equal to, or psi of t rather, for all t greater than or equal to 0. And then at the other end point, at the other boundary point, it's equal to rho of t for all t greater than or equal to 0. So you can call the f and g the initial displacement and velocity. So sort of like an initial condition. And then psi of t and rho of t are like the boundary values in this situation. Okay, so that's our wave equation. The main thing you want to sort of memorize is this first line, and then if you understand, these boundary conditions and initial conditions, you can just think about these. All right, so the next thing we want to show is that the wave equation is in fact a hyperbolic equation. In this case, instead of y, we have t, right, for time, like I said previously. So take this second order PDE and just write it out. So AUXX plus BUXT plus CUTT plus F of XTU UXUT is equal to 0. So in our situation, we can write UTT as C squared over 2 UXX, right? And then just rearranging, we get this relationship here, right? So we get this is equal to 0. And in the format above, then our A will be negative C squared over 2. Our B is 0, right? And our C is 1. So, you can have the A UXX, C UTT equal to 0, where C is 1, A is this number, and B is 0. And then we just compute that discriminant. So B is 0 is 0, 4AC is negative 4 times 1 times negative C over 2, and that's just C squared over 2. And we know that that's greater than 0. And so that tells us that the wave equation is hyperbolic. So we go back up to here. When it's greater than 0, B squared minus 4AC, for this second order PDE, we know that's a hyperbolic. And the reason it's good to know these is because, we've used sort of different PDEs. We've generally used the same core solution technique, but remember there's like little things that you can change, and there's certain algorithms that have been developed for each PDE that you can look at. So in this case, we'll look at some of those. Okay, so the wave equation is hyperbolic. Let me just check in the chat and see if everybody's doing okay. Any questions? All right, so far so good. Okay, so now we should go through how do we sort of approximate a solution to this thing, right? So we have some relationship between the derivatives, and we want to know which functions on our space or on our domain or whatever satisfy those relations, those derivative relations. So, a lot of, if you remember from like ODE, ordinary differential equations, you can imagine your space of solutions to be like polynomials if you want an example in your head, but it goes a lot deeper than that. The functions, of course, are way more general. And in like numeric methods, they can be extremely strange functions. So, but if you need an example to think of, it's good to have those. So we're going to let M be the number of steps in space, and then H will be the B minus A over M. So we want to take some number of M steps in space, and then we want to take sort of the mesh of those steps, which would be the difference of the two endpoints, and then divide that by M. Just like you do in, we've done before with a lot of different things, and you do in Riemann integration. N will be the number of time steps, and K will be just T over N. So that's another variable we define. And then we can define a spatial grid where A, like for example, A is X0, then we have X1, X2, X3, X4, which is B, right? So we're just defining a partition of AB here with these points, and then we have some step size between the points, and also we have some time step as well. So now what we have to do is apply our central difference formulas to get the second derivative. Remember, we can use this, and we'll just use the sort of modified formula for a partial derivative. We're looking at x plus h, u of x plus h minus 2u of x plus u of x minus h in the first variable. And then in the second one, it's a fixed t, right? So then divide that by h squared. So you can get this by playing around with Taylor series, and you can see that it'll be it'll be an approximation of the second partial, uxx. And then we have some higher order terms. If you work out this proof to show this is approximation, the reason that we have the fourth derivative here is because the third one was canceled when you're looking at the Taylor series. between u of x plus h comma t and u of x minus h comma t. And then the condition is just that C1, which is the point we evaluated these sort of remainder terms on, has to be between x minus h and x plus h. So this last term here, the reason I include it is because this is where your error term will come from. So if you need to do some calculations to get the accuracy, that you want, then you'll use this error term. All right, so what I want to do is just go through, how we look at this a little bit deeper. We sort of went through it a little quick with the other two types of PDE. So I want to slow this one down just a bit and kind of look at the same idea, but a little slower. So I've written a little code here, and I'm going to define an x-axis, right, which is going to be my space axis. And then I'm just going to do that, I'm going to give just some points between 0 and 5. I'm not using a big partition, but this will be my space partition, and then give those labels for the plot. And now I'll create a grid, and the grid will be, a grid that'll be the number of space points or space steps by the number of time steps. So the grid's what I'm going to work off of to actually solve the PDE. That's a 5 by 5. So then I create a figure and axis using matplotlib, and then plot filled in dots. You'll see in a minute what I mean by that. I just put some little notes to myself here. For I in range 5, j in range 5, if my grid is equal to 1, right, then I'm going to plot a blue filled circle on that. Then I set my x-axis and my x labels. Right, so that was what I was doing up here. I was creating my labels, and then this will be my x-axis, right? And then I do the same thing with my y, which I just make 5 time points, call them t0 to t4, and then set my limits on my x and my y just purely for formatting to set how big my x-axis is and how big my t-axis is, and then display it as a grid. And let's just go ahead and run this, make sure. All right, so this is the idea. We have our space position down here on the x-axis, which is our interval, and then we have our time position on the y-axis here, and then we have these different space-time points that we'll be able to plug into our function and into our PDE. All right, so that's the basic idea we're using. All right, let me check the chat real quick. Okay, no questions in the chat. Okay, so the next thing that we should talk about are central difference formulas, and in particular, we'll look at the central difference formula in time. Right, so it's just the same formula that we used before. You've got u sub tt of xt, and then this is the fact that we're using this formula comes from the Taylor series that I was, you could prove that with the Taylor series. You just take these two Taylor series and look at their differences, figure out how you would find the UTT term. And it's the exact same thing as I showed earlier, where we fix now, we're just fixing the first coordinate, the x coordinate. And then in the second coordinate, we've got t plus k, t, and t minus k over k squared. And then we evaluate the remainder on some point that's in between t minus k and t plus k. So notice that we're evaluating this time remainder on a point in the space dimension. So this will actually be for each fixed point in the space dimension, we can still vary the time dimension. Okay, and the local error here, local, I mean the fact that we're using like a t minus k, t plus k as an interval, so locally around a point that we choose to evaluate this function on, the area will be the order of h squared plus the order of k squared. And then we have this, we have our space derivative, and then our equation will become will become UTT is equal to C squared UXX. And then using this equation, which is our wave equation, and using these finite difference forward approximations, we get this here, right? Which is really just, well, let's just like go through it. So look at the subscripts, right? So the UTT here on the left, right? So that's the J direction of the grid, right? So I've got J plus 1, J minus 1. And the I direction of the grid is fixed because now we're dealing with like the grid points themselves and the approximations at each I comma j in the grid for, you know, whatever we're looking at. And on the other side, on the right-hand side, we have C squared, right? And then we have the X derivative, but now I fix my J, and then I'm doing the Taylor approximation of y plus 1 comma j, y sub I comma j, and y sub I minus 1 comma j. So that's what this becomes, and this is just the approximation at xitj. So that's what our equation looks like in a written out form where we have data points and values that we're dealing with. Okay, so now let's talk about the discretized equation. Let's check the chat real quick. Okay, so far so good. All right, so we have the discretized equation that I showed you up here, right? So this is the same equation that I have written here. And now I'm going to play around with this just a little bit. So if I set an element sigma equal to ck over h, right? So that's what I'm going to do. And the point is I'm going to try to rewrite this in terms of the next time step, right? So in the first variable, we have the space dimension, and that'll be fixed. And then I want to approximate the next time step, j plus 1 in this case. And that's this first coefficient here in this relation. So what I want to do then is I can solve this using this relation for, you know, I comma j plus 1. I have to multiply through by k squared and then add these term and subtract this term. Right, and then I'm going to use this to get a nice, easy relation here that I can work with. So we'll get yi comma j plus 1 is equal to 2 minus 2 sigma squared yi comma j. And then that would be plus sigma squared yi minus 1 comma j. Right, so that's this term here. And then plus sigma squared yi plus 1 comma j minus yi j minus 1. Right, so the point is, okay, so you have some terms over here that you can work with after you multiply by the sigma. You have some like terms, you have some different terms, and then you can write the next time step in terms of those other terms. And multiplied by that sigma. Okay, so I'm just using what's called the stencil method. I'll show you that in code actually. So this right here is a typo. But the problem is like, okay, so if I start at j equals 0, right, like we've seen in our previous, let me just open one of those just so everybody has an idea of what I mean. Right, so this is how we've been working, right? So we have the two different axes, and then we have our steps, right? So we have if our ij starts here in the middle, in the heat equation case, you could imagine the heat radiating out in different directions. And then I have my I direction, which is like the x-axis as well. And then I have my j direction, which goes, right here, like j minus 1's here. So that's what we're talking about when we're talking about these coordinates. And remember that for each pair, you also would have like a y approximation. And so that's what we're doing there. All right, so let's just kind of go through some code here. I'll just show you. So here I'm just defining a specific ij. I just start at, the origin, for example, and then I will define what coordinates I want for the filled dots, right? And after that, we'll create a figure and an axis that we can plot the figures on. And we'll plot some filled red dots on the figure to show you kind of where our steps are. And then just some notes here. For the x-axis labels, I'll just use the I minus 1, I, and I plus 1. And for the y-axis labels, I'll use j's, j minus 1, j plus 1. For this, I just set ticks. That just means that I'm sort of making a grid. And on the left-hand side, I have -1. Then I have 0 in the middle. On the right-hand side, I have 1. So you can just imagine the x-axis with the integers in that situation. Same thing for the y labels. And then setting the axis limits, from -5 to 1.5, just so it contains these labels that I put on there. So let's go ahead and run this. All right, so you can see what we get here are some different points that we might want to find. And those are all the points in the equation, if you look. So we have, in our equation, we have I minus 1 and I plus 1. And then in our equation, we have j minus 1, and the next time step is what we want to solve for. So we need to use these points in the grid in order to get the next time step. And if you look at what points we have ij, which in the code that I've shown is the origin. And then we have I minus 1j, right? I plus 1j. And then we have ij plus 1 and ij minus 1. So if I go back down here, you'll see that's what we get. So this would be like ij plus 1, ij minus 1, I plus 1j, I minus 1j, and I comma j. So we can use this, and this is what is the so-called stencil method, right? You can use this stencil method to start, right? Because now the next thing we want to do is be able to use the previous points to get the next time step, for example. All right, so that's another one. Let me check the chat. Okay, everybody seems to be okay. No questions at the moment. Okay, the next topic is the tridiagonal matrix. So that's become kind of a big topic in the course. We've seen that popped up over and over again. And then the idea was that the tridiagonal matrix, for one thing, it's a sparse matrix, so it has a lot of zeros, especially you have a big bunch of data. And then also the tridiagonal matrix has convergence and stability properties. So we discussed some of those in some of the previous lessons. So in this situation, we have our discretized equation here that we've been talking about. Remember what our sigma is. And then we have this for I from 2 to m and j from 1 to n. So basically what that does is it takes my grid and it turns my grid points into a matrix, right? So I can parameterize my I points from 1 to m and my j points from 1 to n, right? And the boundary conditions on x for when I is 0 and I is m plus 1, right? So those will be the boundary conditions on X when I is 0 and when I is n plus 1. Okay. So if we put this into matrix form, which we can do by just sort of thinking of, I mean, one way you can do it is to evaluate this at basis vectors along, this matrix here, and then it would just give you the correct coefficients. And you see that's what we're really getting, is we're getting down the diagonal, I get 2 minus 2 sigma squareds, and then I get a sigma squared on the subdiagonal, and then also a sigma squared on the superdiagonal. So that gives me the tri-diagonal matrix. These are nice. It makes it easier to look at things about the matrix, like its eigenvectors and eigenvalues. So they're just nice to work with, and they're especially good for these algorithms because they have good convergence properties and also good complexity properties because they're sparse, or they can be sparse. Okay, so now we showed the time stepping formula when J is 1, right? And we showed how to find the -1. And then the general time stepping formula for J greater than 1 is what we'll show now. Oh, that's a typo there. Okay. All right, so for J greater than 1, right? So we have the same formula that we've been talking about. Y sub I comma J plus 1 is 2 minus 2 sigma squared Y sub ij plus sigma squared Y sub I minus 1 comma J plus sigma squared Y sub I plus 1 comma J minus Y sub I comma J minus 1. This formula, if we use matrix format, right, as we saw before, we have this formula. Okay, so now let's just stop and kind of go through this formula so that we can understand what's going on. Okay, so I have here, look in the first variable here, I have Y sub 1, Y sub 2, all the way down to M minus 1 and M, right? And then in the second variable, I have J plus 1s just fixed, right? So this is telling me my next, my J plus 1 time step, just like this is. So that's the same sort of idea here. But this encapsulates the whole system, right? So this will be equal to A, which is some matrix, times this vector here. So look at what this vector is. It's, again, in the first variable, we have Y sub 1, Y sub 2, all the way down to Y sub M minus 1, Y sub M. And the second variable is J, right? So we're taking the matrix, we're multiplying it by the previous time step, right? We're trying to get the next time step when J is bigger than 1. So we take a matrix, multiply it by the previous time step, and then we subtract something. So if we look at what we're subtracting, it's the same idea, Y sub 1, Y sub 2, down to Y sub M minus 1 and Y sub M. And the J sub minus 1s are fixed. So we're subtracting the previous vector from the previous time step. So this is actually going 2 time steps back in this formula. And then in the final one, we have our sigma squared times this vector here, which this vector is really just encapsulating the boundary conditions, right? Y sub 0 comma J, Y sub M plus 1 comma J, and then multiplied by sigma squared. And the matrix A here is the tridiagonal that we saw before. And then the boundary values in reality, so those will be a function of T. And I meant to call this L. Oh, shoot. I meant to call this L, so it's a little bit of a typo here with this apostrophe thing here. But it should be, so Y sub 0J, which is the first component of this matrix that we're multiplying sigma squared by, is some function of T sub J, or the value of that function at T sub J. And Y sub M plus 1 comma J is another function evaluated at T sub J. So the matrix is the tridiagonal, and the last component that we're adding on is the boundary conditions. And then the other ones is the difference of the previous time step with the time step before that, where you take the previous and multiply it by the tridiagonal. And that gives us the next time step. Okay, so hopefully everyone followed that. Let me check the chat, make sure nobody has any serious questions. Okay, so I assume everybody's following okay. Let me go ahead and continue. So now we have for y greater than 1, and we want to determine, exactly what is y negative 1, whatever that means. This should be a subscript, and the actual boundary conditions. Okay, so remember, we'll work on the interval a, b, and we have the finite differences for boundary value problems, and we have our pairs of points here that we're dealing with between a and b, right? And somewhere over here we have y negative 1 and x negative 1. So that's what we're trying to determine, the y negative 1 term. All right, so how do we find it? Well, if we go to the central differences for y prime, then what we'll see is if we take y of a plus h minus y of a minus h all over 2h, that will give us an approximation for y prime at the point A, right? And another way you can think about that is if you look at what these are and you imagine that a is 0, like, when y of 0 is what a is, and then if I add 1 to 0, that would be y1, and then if I subtract 1 from 0, that would be y negative 1. So that's the first sort of idea that we want to use to try to determine this y negative 1 and how we get that. All right, so let's apply the idea to yi comma negative 1, right? Because we've been working in these pairs of subscripts, so it kind of doesn't make sense to just say y negative 1, right? So what do we mean by that? Well, the negative 1 time step, right? So I have y sub I comma negative 1, and it's just the time step before 0 that we're looking at. So if we apply this idea, this simple idea here, to our functions that we're looking at, then we know that the time derivative evaluated at xi at time 0, right, can be written like this. So in this situation, my a was 0 plus k, 0 minus k, because this is the time dimension, the second coordinate. So evaluate u at xi comma k and subtract u of xi comma negative k divided by 2k, and that'll be our u of I comma 1, or I'm sorry, y sub I comma 1 minus y sub I comma negative 1, and that's equal to 2k. And that's the condition. Remember, u of t has a boundary condition at 0, by the definition of our actual PDE that we're working with. And remember, it was g of xi. So u sub t of xi comma 0 is equal to g of xi, but using the finite difference methods, we see that that's equal to y sub I comma 1 minus y sub I comma negative 1 over 2k. Okay, so hopefully you understand where that comes from. So we just solve for y sub I comma negative 1 to find it, and what do we get? Well, it's equal to y sub I comma 1 minus 2k times the function, the boundary function evaluated at xi. Okay, so that gives us exactly what that is. All right, so in the top condition, or in the top case, we use this constant sigma so that we could have a nice relation like this, and we use the fact that this relation was so nice to create a tridiagonal matrix. Okay, so the relation defines a tridiagonal matrix. And then to get the time stepping formulas, to get the next time step, we just multiply through this equation, this vectorial equation, this matrix linear algebra equation. That was for whenever j is greater than 1, right? So j negative 1, then the question is, how do we get that? Because we're starting at 0. So to get the negative 1, which we would need here, right? If j was 0, then we would get j is 1. 0 here, we do have the data on that. But here's where we're in a situation, right? So this, if it's negative 1, then we're in a situation. So that's why we want to find these y sub m or y sub I comma negative ones because of this vector here for the j equal to 0 case, right? So we don't really have a j equal negative 1, but that's sort of the case, right? And to find the negative 1 case, we use this schema here. So we have our intervals, we have our general idea, which this is where the idea came from, and then how do we actually compute it? We do have that boundary condition, so that's actually where we can compute this. All right, so yeah, let me check the chat and make sure everybody's following along. Okay, this seems like maybe a good time to take a little break. So I'll come back in like 10 minutes or so, and we'll continue. Let everybody get a drink and use the bathroom. All right, so I'm back. So let's go ahead and get started. Okay. All right, so we had just figured out how to find y I comma -1, and we also figured out how to deal with when I was greater than 1, or j was greater than 1. So for j equal to 1, we have a matrix form of the time step as well, and you'll see how we'll write that out. So for I goes to 1 to m as usual, we have, if we just plug into the equation, we have yi comma 1, and that'll be 1/2 of 2 times 2 sigma squared yi comma 0 plus sigma squared yi minus 1 comma 0 plus sigma squared y sub I plus 1 comma 0 plus 2k g of xi. So that's how we find out 1, and we have another matrix form here, and you'll see that this is going to be a little bit different on this boundary term. So it has this extra term. So to get this vector here, y1, 1, y2, 1, all the way down to m minus 1, 1, m1, we can take 1/2 a. A is the tridiagonal that we saw before, and y sub 1, 0, 2, 0, m minus 1, 0, m0, and then 1/2 sigma squared, y0. So we're adding, in both here, and also we have the 1/2. Y0, 0, zeros everywhere else. Y sub m plus 1, 0, sort of like the boundaries, you can think of it there, and then plus k, and then that function g that we're given as a boundary function, evaluated at x1, x2, all the way up to x sub m minus 1 xm. So this is the matrix form for when j is 1. And the boundary values that we get are y0, 0 is L of t0, and y sub m plus 1 comma 0 is R of t0. All right, and okay, so I just want to sort of go through a little bit of code here and sort of show you how this works. Okay, so initially this was written in Julia, but it's in Python here, so let's go ahead and go through it. All right, so I'm defining a function here that is the wave differential equation, or the wave PDE, and you saw that. Let's go back to the definition just for a second, just so we can remember all of the different conditions on this one equation. So here it is. So the second time derivative has to be equal to this sort of c squared number, which we defined before as, I believe it was the wave speed or something, right? So I don't remember exactly how I worded it. Okay, so we have c squared, which is some constant, times the second space derivative, and that has to be true for every x and all t greater than or equal to 0. And then we have these, the next thing are the two initial conditions. So we have, at the initial time, we have a function that describes u of x, and then at the initial time derivative at 0, we have a function that describes u sub t of x for all x. And then finally, we have the two boundary conditions. So we have something defined when we're at the left-hand boundary when x is equal to a, and the right-hand boundary when x is equal to b, and these will be defined for all t. So just keep these in mind. And we're using the fact that we have all these relations, even though it seems messy, we're actually using these relations to get actual results about the equation. So they come in handy. All right, let's get back to the where we were. All right, I think we were here. So that's why I have all of these values in this function. That's why I wanted to point out to you. So I have a C, which describes, it's that constant that I'm using. I have my F0 and my G0. Those were my sort of initial condition functions. And then I have a left boundary and a right boundary, which were my boundary functions. I have the range of my interval A and B. I have a time parameter T. And then I have the size of my matrix, or the size of how many X values and how many T values I have. Okay, so those are all the inputs for this wave differential equation function. But we'll go through and try to determine some solutions using the technique that we previously described. All right, so my result will just be an initialized matrix of size M by N. It'll start out as zeros, and then I'll have an offset matrix of size M, right, which will also be zeros. Now, this is because this is the thing I want to add, right? So I'm going to add that to a matrix of size M by N. So if I multiply vectors in that matrix, I'll get vectors of size M. My time step, my H, which is my space step, I can think of it like that. The mesh of my partition in space will be the difference of whatever B and A I choose, and then I'll divide that by M plus 1. So that'll be, we'll have M plus 1 different variables. So the same thing for my time step, I'll go whatever my time is divided by N minus 1. That'll be my K. So those are my mesh for the the mesh size or the step size, or however you like to think of it. It's the size of the intervals, like when you learned about Riemann integration. It's the size of the little delta x's. It's just that we have a delta x in the space direction we can partition, and we have a delta x in the time direction. And the mesh is sort of the maximum width of one of those delta x's, because it might not be evenly spaced points. Okay, I have my sigma. That was defined previously to be ck over h. And then I'm going to create my tridiagonal using that sigma and these other values. So that'll be 2 minus 2 sigma squared times an m-dimensional vector of 1s. And then the subdiagonal, remember, were sigma squared times a vector of m minus 1. And I'll just pick out what I want to go in that vector when I create my matrix. And so when I create my matrix, I have my diagonal. So I'm going to take a diagonal matrix with this, and I'm going to add to it the subdiagonal, right, where I have another diagonal. And let's just show you here, if we go into the, if we use the parameters here, the k is the diagonal in question. So the 0 is the actual diagonal. If we want to do diagonals above the main diagonal, we just do k greater than 0, and below the main diagonal for k less than 0. So that's why this k is here. So I take so that creates a diagonal plus a super diagonal, because this would be above, and then plus or was it the other way? Anyway, so plus above diagonal plus a below diagonal. That gives us our matrix A, and it's just exactly the matrix that we worked out before when we were working out this equation. The result, okay, so these are the different vectors for the matrix, right? So my result will be my boundary function evaluated at I times h for all I in range 1 to m plus 1. And then I have my g function, same sort of idea for all I in range 1 m plus 1. And then I have my offset vector, as we saw before, which was 1/2 sigma squared times, remember the endpoint was my left boundary evaluated at 0. And then I have the offset at m-1, which is 1/2 sigma squared times my right boundary evaluated at 0. And then the second piece of my result will be just to add a times my previous result plus my offset, right, plus k times a vector, which is these g vectors here. So in this line here where this result is, if I go back up, it's just this, right? So these are the k times the g vectors. All right, that's the last part. The next one was offset. So let's see, if we have offset, we have 1/2 sigma squared, and then the offset was my left boundary, my right boundary, right? And then the one after that was take the tridiagonal we created and multiply it by the result, which in our situation will be these approximations using this whatever function f and g we have. So that's what we're getting there. And finally, I run down through the time parameter, right? So for j in range 1, comma n-1, my offset will be sigma squared times my left boundary. Offset at the last point will be sigma squared times the right boundary. And then the result evaluated on the time steps. Remember how we approximate the next time step was by using this matrix here, right? And then I'll return whatever my result is. So that's the function that will actually do all of this stuff that we're just talking about, if you want to play around with that function. All right, so that's this. And then, okay, so I've defined the function, but I haven't shown you how to use it, right? So let's go ahead and do that. And in this situation, I'm just going to define all of the functions, just play around with different functions and plug them into that and then run that through, and that'll give me a solution to some wave equation, right? So when c is 2, I'm going to make that my c. My a will be 0, my b will be 1. So I'm just going to use the unit interval from 0 to 1. My maximum t will be 1. So I'm going to go from time parameter from 0 to 1. And then I'm going to do 20 space steps and 50 time steps. So it'll be a 20 by 50 matrix. My initial condition function will be sine times pi. Right, so f of x is sine times pi x. My initial condition for the velocity or the time derivative, I'm just going to make 0. I'll make everything else 0, so this is easy. But this is my initial time derivative or velocity function. I'll just 0. On the left boundary, it'll be the constant function 0. On the right boundary, it'll be the constant function 0. And the solution to my wave differentiable function to solve the wave equation will be this, right? So I evaluate all my functions and I plug them in here and I'll solve my wave equation. We went through that previously. That was we'll use this wave diff function to solve the actual wave equation. All right, and then I'm just going to create a grid. I'm going to plot my x's and my t's. My x's will go from a to b of size m. My t's will go from 0 to t of size n. And then I'll make a mesh grid so that I can actually plot this in 3 dimensions. Because I'll need the mesh grid to use this plot surface function here. So I'll define a figure. I'll make the projection 3D and plot a surface of x, my time, and t. And then I have to use the transpose here for my third part of the surface just so all the dimensions match up. But that's my result, my solution. And then I just create some labels, xt. The z label would be xt, and then the wave equation solution. So, all right, so the wave equation that we defined previously, where we said, okay, so we have the boundary functions. This is what we want to say that they are. We have the initial condition functions. This is how we would say that our wave wants to start. And then it gives us the function u, which solves those and solves the PDE, and then this u looks like this in this situation. So, all right, just as a little, just as a sort of something to notice, the picture was made with m is 20 and n is 50. So if I look at the n equals 25, right, if I plug that in, then what we see here is this last column is going like sort of more and more negative, right? So it's like, it's kind of not stable, right? It's like not conditionally stable. So it's kind of all over the place. So what we want to do is find some kind of a critical threshold for this, right? So to show that our algorithm can be stable, and we want to find out how to do that, and we'll kind of look at that. So let me just check if there's any questions before we continue. Oh yeah, so lesson 8, I believe that lesson 8 was sent, so you can ask the other instructor for lesson 8. Yeah, I sent that out. Thanks for the reminder, though. I might forget. All right, so let's go ahead and continue with the find the critical threshold. All right, so this was the wave equation that we were looking at. So in this situation, C was 2, right? And we saw how to get an approximate solution for this. And the one I had written before, if you remember, was this function here. My initial position function was just sine of pi x for all x in AB, and then everything else was 0. And that was, so this was the partial differential equation that we were solving for in the picture, right? And so this is a PDE, and that was its solution. So that gives you sort of, you know, if you see a different PDE, then you can use that technique I showed you to find its solution. So if I set m equal to 20, right, make a smaller m, I just want to do an experiment to find the smallest value of n, so the smallest matrix by 20, for which that makes this thing appear stable. So in this situation, if I change n to 25, it doesn't look stable. Okay, so hopefully that's clear. And to do this, let's go ahead and do a little error magnification study. So remember that if j is bigger than 1, we have these time-stepping formulas, right? We went ahead and solved j equals equal to 1, equal to 0. So we have other ones too, but if j is bigger than 1, we have this one. And this one is, you know, the same one we've been looking at. If we want to write it in matrix form, then we can write it like this: a yj, yj minus 1, right, sigma squared sj, and that's where sj holds the conditions at the boundaries. So this is a really sort of concise form. It's basically saying that the next time step is equal to some tridiagonal times the previous time step minus the time step before that, plus some constant squared, so it's a positive number, times some vector that holds information about the conditions at the boundaries. Okay, so we want to study how the error magnifies, so we can play this little game with this. And what we can do is just look at it like, okay, so yj plus 1, yj as a vector, we could think of this as, rewrite it like this, right, as a vector. So a minus I times yj minus 1, zeros in that one, and sigma squared times sj 0. And all I've really done is just added some zeros in the bottom, but I'm using this, if you look at, you know, the matrix multiplication here, you'll get ayj minus yj minus 1, and then, yeah, you'll get the same thing here. So that has to be equal to this. Now, for this to be stable, because this is now just a linear algebra equation, the eigenvalues of this matrix have to be bounded by 1. And in the previous example that I showed you, the largest eigenvalue was 1.08 times 10. So that's a little bit bigger than 1. Okay, and that's what it takes for the method to be stable. All right, so I'll continue. Yeah, so this is, okay, let me just, before I continue, let me just check for questions. All right, so far so good. Okay, so now we know we have a condition for it to be stable. The eigenvalues of this matrix, not the eigenvectors, the eigenvalues, have to be less than or equal to 1. So that's going to depend on, you can, if you want, you can find the eigenvalues of this by solving an equation and then determine out, you can even sort of play games with what they should be. But in the previous example, we got something bigger than 1. All right, so now we have the CFL condition. And this is going to help us apply these ideas and to understand the answer to our question. Okay, so let me just say a theorem. Consider the wave equation over x and AB for t and 0t. C greater than 0 with h equal to b minus a over m and k equal to t over n. All right. If c times k over h is less than or equal to 1, then the finite difference method is stable. The quantity c times k over h is called the CFL number and named after Courant, Fredericks, and Louis. Okay, so we have the CFL number, c times k over h, is how we can tell if this finite difference method is stable. All right, so this is another way of saying ck is less than or equal to h. So this condition, right, if we just clear fractions here, for h positive, then this condition, c times k is less than or equal to h, is known as the CFL condition. For our example that we've been working with, right, a comma b is equal to 0, 1, and 0, t was equal to 0, 1, c is equal to 2, right? If we do m equal 20, then h is 1 over 20, right? N is 50, as we saw before, and then k is 1 over 50. Then c times kh is 2 times 2 over 50, which is less than 1. But if we do m equals 20 and n equals 25, right? So m equals 20, h is 1 over 20, right? That would be like the mesh size. K is 1 over 25, like kind of, the b minus a over n deal, because everything's zeros and ones here. And then c times k over h is 2 times 20 over 25, and that's greater than 1. So that's why we saw in the first, or we didn't look at it, but in the first situation, there was stability. In the second, which we had right here, there was not, right? Because we had that this CFL condition was greater than 1. So that's the point of this. It tells us information about the convergence of this algorithm that we've been talking about that solves the wave equation. All right, so yeah, so we'll look at this for a second. Let me just check for questions. Okay, so far so good. Let's continue. Okay, so what if we want to actually apply this? Then we consider the equation with a wave speed of 2, and of course that's what we've been looking at, right? So I wrote it out a little different this time just to give you, something else to look at. but we have del 2u del t squared is equal to c squared del 2u del x squared for all x in AB. So this is that UTT equals UXX times c squared. That's the first condition for the wave equation. And then my function u has to satisfy all of these other relations as well. So in our situation, the first initial one was sine of pi x. So that's the function it's initially equal to. And then the initial time derivative at 0 was 0. So in that situation, I guess it could imply that it has to be constant in, this one time dimension here. And then everything else was 0. So the boundary conditions at A and B were both 0 as well. So that's what we're looking at. Now, so let me just go back up here. So here I showed two examples of using the CFL condition to show stability in this algorithm. Okay, now I will show for m equal to 20, so the same place that we've been, m is equal to 20. I want to apply the CFL condition and find the smallest value for n for which this, so I want to minimize this condition now, right? To say this is the smallest n we could have to make it stable. And you, of course, can see why that's important to do, because we want to minimize the number of operations that our algorithm takes so that it can be less complex and also faster. So this is one way you can do this. All right, so the solution, well, you know what, I'll let you I'll give you a few minutes to think about this, right? I showed you how to calculate. I'll leave this line here, and then so think about this and try. I'll give you just a few minutes, and you can say what your solution is, or see if your solution matches the one that I'll show. Okay, so that's probably enough time to see what we get. All right, so let's see how we do this. So the CFL condition says that C times K over H has to be less than or equal to 1 for stability. And remember, C is the wave speed, K is the time step, and H is the spatial step, right? So K is the mesh for the time dimension, H is the mesh for the space dimension. In this case of this PD that we set up here, we have C is equal to 2, and we're given that M is 20. Okay, so H in our situation is B minus A over M, which is 1 minus 0 over 20, which is 120. And we want to find the smallest value of N, so we need to find a K such that this condition holds. Right, so here's what we'll do. I'm not going to substitute in K, right, because we don't know what K is. So I can make a function 2 times k divided by 120, and I want that to be less than or equal to 1. So simplifying a little bit, I get 2k is less than or equal to 120. I just clear fractions on both sides. And I get k has to be less than or equal to 140, or 1 over 40. So the smallest value for n for which the method appears to be stable is n greater than or equal to 40. So if we want to ensure stability, we should choose our sample size n, right, to be greater than or equal to 40. All right, so let's see if there's any questions. See how everybody's doing. All right, so hopefully that was the answer that you got. But in either way, you can see how if we're given these numbers, you can just do a little bit of calculation to get the correct value that you should choose to ensure that the CFL condition holds, and then that'll ensure stability in your algorithm. Okay, so now, yeah, we can do a little bit of computing for a faster wave, right? So let's do c equals 2, and we'll compute the solution using the wave diff function that we talked about before. So remember that had 2 as our c. We had a f, a g, which were our sort of initial conditions. And then we have a left boundary function and a right boundary function. And those were our boundary value or boundary conditions, boundary values. And then we have our a, b, 0 to 1, and our t, right? So time will always start at 0. And this big T is just where we want to end at, our maximal time. And then this was the matrix size that we were using, right? So if we use this, and then we look at the CFL condition, C k over h is less than or equal to 1 to ensure stability. And then we look at this where we change something, right? So I'm going to change my constant C to 6. So it was 2. I'm going to change it to 6. And then I'm also going to change my n threshold also 3 times. So I want to see what happens if I do that. If I make my wave speed faster, so that's the faster wave, and then I triple my my step size for my n. So in this case, we have c is multiplied by 3. We also increase n threefold from 50 to 150 because k is t over n, right? Then we decrease k from 150 to 1 over 150. So k goes down as we change the speed of our wave. And that's, so the idea is that we made our speed 3 times faster, but we didn't want to change the problem too much, so we scaled our point in the same way, 3 times in our n. We increased that by 3 as well to give it some unit of consistency. All right, so yeah, so I'm going to show you, how to plot these two. So this was the idea. So let's go ahead and find the solutions. Okay, so first thing is I have my libraries, matplotlib, that's what I use to plot, and then I imported this like plot 3D feature as well. And just like before, I'm just defining my function. So my FG left boundary function and right boundary function, you could change these if you wanted. And then my function is the same one as before, the sine of pi x. And then everything else is 0. So my derivative function for time is 0, and my left and right boundary functions are for time is 0. When t equals 0, this one's 0. When t equals 0, this one is sine of pi x. And then the left and right boundaries, when x is equal to a and x is equal to b, those are 0 as well. Okay, so now I compute the solution for c equals 2. That's just taking these functions I defined, putting 2 in for c, as you saw up here, the wave diff function, same kind of idea. So I've got 2, fg, left boundary, right boundary. My space interval will be just from 0 to 1. My time interval will be from 0 to 1 as well. And then I have my m and my n, right? So m and n. 20 and 150. And then if I want to do this for c equals 6, I just put a 6 here. Everything else is the same, but I scale my n dimension by 3 as well. So I make that 150. After that, I created a 3D surface plot for c equals 2. And to do this, I use the mesh grid, because if you're doing 3D stuff, you need to use a mesh grid, like an X and a Y or X and a T. And then what I'll do is I'll just take two, like I'll take a space parameter, which is just, numbers between 0 to 1, and then however big this shape is. So this is some solution that'll have a some m by n shape, 20 by 50 or 20 by 150. So I want this to be a vector of however the shape in the second component is. And then in the first component, because numpy index is from 0 instead of 1, so this is the first component, which is my t component or time component. I'll use the first shape. So so if you want to think of it like this, this is the time dimension, this 20s, and then the space dimension are the 50 and 150. I'll plot the figure after I use this mesh grid, and then I'll add some more plots. So 1, 2, 1 will tell me this will be the first one in a plot of two things. Tells me to use the 3D projection, and then the actual thing that I want to plot is the mesh that I made. So I have the X, the T, and then the C2 solution will be my Z coordinates in this mesh. Give it a color and set some labels, X and T, and then a title, solution for C equal 2. Same situation with the when C is 6, same space, right? Solution C6, that'll be 150 in the X variable dimension. And then in the Y or the T dimension, it'll be 20. But I'm just using a more general code here. And then we'll take 150 points between 0 and 1 in the X dimension, and 20 points between 0 and 1 in the T or time dimension. Add another subplot. So this will tell me it's the second plot in my little plot. And then my projection, same thing, except now I'm going to use solution C6, right, when C is 6 instead of when C is 2. Give it a color, make some labels, and then a title for when C is 6. And then show that all in the end here. So let's go ahead and run this and see what happens. All right, so there's our two solutions. So when C is 2, we get it's not as fast of a wave. It doesn't go through a full cycle as fast. But when C is 6, you can see we get a lot more cycles in the same sort of span of time. Right, so that's kind of the idea here. So you can imagine that this is an initial condition as a sine function, and then the time, is going the sine function will be over here rather. And then as we move through time in this dimension, that's sort of what the relations in that PDE are describing. Like if we start with some function, and then we have the condition that the space position is 0, the time derivative is 0, and the boundary conditions are 0, then we get something like this that moves through time, and we're describing each step of that using those conditions, well, with the algorithm that we laid out. So, and the same idea applies here for SQL 6. Here I just, well, you know what, I'll go ahead and just pause for a second and see if there's any questions. All right, so far so good. We got a little bit of time left. Yeah, so this is just another version of this function where instead of using three-dimensional, I just use like some regular like heated kind of heat plots to describe the z parameter here. So same thing, solution for c equals 2. I don't feel that these are as informative. But you can see here I have solution for c equals 2. And then what it does is instead of using the three-dimensional functionality of the matplotlib, you can use this bar here, and it'll tell you like the values. So the higher values are in yellow, going down to the darkest, almost like a deep dark blue. And then you can sort of view it like that more topographically, I guess. So you can see this, when C is 2, the wave has 2 peaks, you know, one here, and then one valley here in the middle. When C is 6, you see that the wave has more peaks. So 1, 2, 3, 4, and then 3 new valleys down here. So, you know, you get different ways to look at it and how it's propagating as we change this C value. And, you know, generally, if you can sort of imagine these are, for each time, it's kind of like a sine function, right? At time 0, it's sine, and then it moves through here, but like with these peaks and valleys. And then for each x, you know, it's just some like level set of that sine function. Okay, so the last thing I want to do today is just look at a little bit of this. Okay. Just check out this parameters and initial conditions for the wave equation. So just like play around with it and sort of get an idea of how it changes. But it seems that yeah. Okay, I think it's about time to stop. So I'll show you this at the beginning of the next course, or the last class we have. It's about, I don't want to make you guys late if you have more classes. So I'll show that at the beginning of the next lesson, which will be our final lesson. And, you know, we'll do some more talk about some numerical method stuff. So everybody have a good rest of your day. I'll see everybody next week for our final lesson, and I'll send out tonight's notes, and hopefully you guys will get those soon. So goodbye, everyone.